any further ado, I'm just going to say, just as a starter, I'll just say, I agree with everything, of course, that Professor Fan just said. I do think we're at an incredibly interesting crossroads in the field of metallurgy, where not only is there a need, like he said, for in the next 20, 25 years to produce a new kind of metallurgy, but I actually think we have the capability of it. There's a whole series of developments which gives us a whole series of new potential, and that's what we're going to hear about, the new ideas, so many of the things which I learned as a student in the 50s and 60s, and some of you will have learned as students, some before me and some afterwards, many of those things are being re-looked at with new tools. So there's a great potential for developing new ways of thinking about our subject, which I think for a long time hasn't really been the case. There've been improvements, but suddenly there's a whole vista of new opportunities. And we need that to meet the need that Professor Fan's mentioned. So we're going to hear about a lot of those things from our speakers. So we're almost dead on time now, so I'm going to introduce our first speaker. It's Professor Diran Apelian. I met Diran a long time ago, longer than I care to remember, but he still looks like he's too young to have been that long ago. But anyway, he's Professor of Material Science Engineering at the University of California and Director of the Advanced Casting Research Center. I think it's at UC Irvine. And he's going to talk about the role of materials for sustainable development in the 21st century. You hear what Professor Fan was saying. Criticality, life cycles, and solution pathways. Diran.
Thank you, Brian. Thank you. Good morning, everyone. Happy to be here. I think with the introductory comments that have been made, many of us here either have white hair or no hair, but this really is for the next generations to come. It's really for my grandchildren, if you will, that the issue is really quite dire and it's time for action. So hopefully what I'd like to do in this presentation is really to talk about that. One way to predict the future is to make it. So we have a responsibility here during this conference. I noticed that it was called a debate. Usually debate is something that you vote on and you come up with specific recommendations that we agree on. So I look forward to tomorrow afternoon's event and the panel discussion and what recommendations will come out. So I think we're here at an inflection point and an opportunity for us to come together and to, as a community, to chart, to create a roadmap of what needs to happen. Some of it is already happening now, but perhaps not fast enough. On a personal note, we're commenting a bit earlier, John Perepesco and Marty Glicksman, that when I was a young assistant professor at Drexel University, when I first met Brian, one of my first trips was in Argentina, where the three of us went to that conference, and here we are 40 years later. At that time, we were more interested in developing new materials without really worrying about recovery or reuse or sustainability. But today, it's all about that. For me, on a personal note, it happened really in 2003 when I had to give the TMS ASM Distinguished Lecture on Materials and Society. I had no slides or anything of that nature previously, so I had to start from scratch. And it was a reflection point at the time where I realized that much of the effort that has been put into place was making new materials, designing new materials, but not so much on how to recover and reuse it. And yet that talk was more focused on population growth. We entered the 20th century with 1.6 billion people and exited the 20th century with 6.1 billion, so tremendous growth in 100 years. And it was really looking at the consumption rates and things of that sort. But those pillars that you see there are really the hierarchical needs of society. Those are the things we need as society. There's like Maslow's needs for living. And materials plays a role in every one of them. 5 years thereafter, we established the very first center in the U.S. for materials resource and recovery called the Center for Resource Recovery and Recycling with Colorado School of Mines, KU Leuven, and then Tokyo as well thereafter. And I think we did quite a bit by getting the industrial sector together, focusing on recovery and reuse of materials, but mostly production waste and post-consumer waste. In this presentation, what I'd like to do is really talk about the path forward. Obviously, in a 30-minute period, one cannot cover everything, but what I'd like to do is really talk about 3 areas that I think all of them need to be pursued in parallel. It's not just technology, innovation, research by itself. Policy has a very large role to play, as hopefully I will make the point in this presentation, but also education as well. We're talking quite a bit about metallurgy here, but as I look at the curriculum at many of the universities today, especially in the U.S., there's not much metallurgy within the curriculum. And many of the students who graduate have no clue or an idea where the ores come from, how do you extract them. I'll talk a bit more about that when I talk about the educational recommendations that I like to make. So my presentation will really deal about pathways forward in 3 areas. But before I do that, let me set some context here. I think some of these things many of you know, but in the first presentation of a meeting of this sort, I think it'd be important to establish and to make sure that we're all on the same page. What I'm plotting here is about 10 years old data, or maybe 12 years old data. It's annual production versus years. And what you'll note is, of course, the units are different. Gold and steel are going to be characterized in different tonnages or carats. But nevertheless, what you will see is a very, very large increase in metal production. Of course, consumption, population growth, all that makes sense. Now, if we have the data for between 2020 and 2025, later on you'll see a small blip due to COVID, but nevertheless, in the long range of things, it's going up exponentially. At the same time, the ore from which these metals are produced, the grade of the ores are also decreasing. So if you look at, for example, zinc, or you look at gold, the red one I believe is gold, or no, that's copper. The grade of the ores are decreasing, meaning you've got to dig much more to get the same amount of metal from the ore. So whenever 2 things go in opposite directions like these, it's not sustainable. This is not a way that you can maintain this. At the same time, if you look at the 2022 data, 2021 data, it's only a couple of years old. Couple of numbers to point to. 2.8 billion tons of metals were produced, 2.8 billion tons, of which 2.6 of it is iron ore. Copper and chromium and aluminum is 68 million. Copper, 21 million. So iron is a very, very large percentage of the total amount. So previously what you saw here is really production, not necessarily by tonnage, but how the tendency or where the vector is going, whereas the most recent data shows the tonnages. So we're consuming quite a bit of metal. Changing topics and looking at the electronics and devices. We all love our computers, etc., and devices. The computer chip alone, and this is from Intel, in a period of 20 years, it went from utilizing about 11 elements to today, I think, over 52 elements of the periodic table. So we're using more and more of the periodic table. And for this audience, I don't need to remind you that many of the elements that we're using today in the periodic table are not abundant, especially the lanthanides all the way at the bottom there. I made the mistake actually, this is from 2010 data, but unfortunately the 2015 data doesn't look very different. But if you look at the end-of-life recycling rates, less than 1% for the lanthanides at the very bottom, 10 to 25% for gold, cadmium, tungsten. These are not acceptable numbers. We have to do much, much better than this. Then if you look at renewables, e-mobility, defense and space, just look at the very middle. Batteries, fuel cells, wind, traction motors, PV, robotics, drones, etc. What you'll note is a Sankey diagram where on the very far left, this is from Dirk Rabe's recent paper of 2022, where there's a very high criticality, if you will, of the rare earth elements, followed by magnesium, niobium, germanium, etc. But essentially material criticality. So I think you get the point that looking at the periodic table that I just showed, that many of these materials are not abundant. They're critical. The other topic, which is a topic by itself, another talk in itself, is the production waste. There's so much production waste right now in producing metals from the ore itself, using old metallurgy processes, and hopefully we will be coming up with new processes. And I know we're going to hear from Dirk tomorrow morning as well. But there's a lot of production waste. What you're looking at here are the red mud, for every 1 pound of aluminum or 1 kilogram of aluminum, you have 4 kilograms of red mud produced, which is also a tremendous resource. Right now it's a waste, but the idea is to take waste and to create value from waste. Post-consumer waste. The amount of waste that exists today. The one anecdote I like to use is that when I teach a seminar to the freshman class, the first year students coming to the university, and by mistake one day we talked about shoes, and it dawned on me that none of them knew what a cobbler is. They had no idea. This generation, the young generation, they just, they don't know what that means. Resoling a shoe is a very strange idea. You throw it away. So the post-consumer waste is and this is where policy comes in. This is where Pavlovian behavior comes in. I got this from Randy Kirchain at MIT. It's a wonderful painting, but what the artist did is he took beverage cans and actually put a collage together. And there's just so much wasted. We're seeing more and more where people are carrying their own bottles and they're refilling them rather than consuming them. But the rate of reuse of beverage cans in the U.S. is about 51%, meaning 49% does not get reused. End-of-life goods. Again, another topic by itself, but hopefully we'll touch upon it throughout today and tomorrow. How are these materials and metals that are utilized in these devices and components and goods are being recovered and reused? So tremendous amount of opportunities in post-consumer waste. The whole idea is take waste and create value from it. Perhaps the most existential problem right now is global greenhouse and gas emissions. I think Professor Fan referred to it earlier in his comments. But the most recent data is that we're producing as the planet Earth about 59 gigatons of carbon equivalent. Carbon equivalent, of course, includes not only CO2, but CH4, fluorine gases, etc. That 59 gigatons is broken down into various segments. 12 gigatons of the 59, which is a significant percentage, comes from industry, industrial utilization, of which iron and steel are about 24%, cement is almost 20%, aluminum is about 6%. So if you look at steel, aluminum, and cement, it's almost like 50% of the industrial sector. So 3 elements alone. Of course, there are other things, titanium and all those. I'm not mentioning them, but so we have as Professor Fan pointed out in his comments, we have a real opportunity here to make a difference. A real opportunity. Of course, the developments of materials also comes into the transportation, agriculture, etc. Okay, so I think hopefully by now I've set the context. Let's talk about some of the recommendations going forward. In the educational domain, let me step back for a second. One of the things that I'm seeing, and I'm not the only one who is observing this, I think I have a lot of colleagues who agree with me, is that metaphorically speaking, we're educating our students to become chefs, but we're teaching them through cookbooks only. They never get into the kitchen. So we have a lot of students today who are not getting their hands dirty, if you will, and we're robbing away from them that joy of learning when you have the experience of working with your hands. I know it's personal, but for me, when I did glass blowing with my wife, I learned viscosity much better than I learned from the diagrams of viscous behavior. There's a certain human dimensional experience when you're working with materials. So that's as a prefatory comment, I think that's one of the things that we're not doing enough as a collective whole, where students are either interning or using the labs and just doing things with their hands. Extractive metallurgy, I know I'm not 29 years old, but I don't feel like ancient either. But I remember learning about flotation by actually doing the experiments of flotation. I remember seeing crushers. I remember learning about ore. It was exciting. So where all these metals come from, where all these materials come from. Much to my dismay, a lot of students have no clue about ores, where they come from, what is the, and I think, many of the technologies for recovery and reuse are extractive metallurgical processes. The Pourbaix diagram is not a new thing. The Ellingham-Richardson diagram is not a new thing, but many of the students today, especially in material science and engineering curricula, and many universities that are very focused on material science, not so much on the metallurgy, a lot of students know a lot about the Fermi electron energy levels, but have no clue about these things. So we need to be aware of this. We cannot be in denial. So if we're going to have students who are going to be graduating from material science and engineering curricula and are going to play a role and be in leadership positions to do something about sustainability, they got to know these things. Supply chains. I was tracking rare earth elements in terms of prices, and there was a period in 2016 where cerium went up by 450% in price. It's not just tensile strength, it's not functional material properties, geopolitical forces, criticality, supply chain. So if these things are not even mentioned or discussed, and the students are not aware of it, we're robbing them from that from being educated. Material selection. Much of the material selection today, if you look at how that's being taught at universities, toxicity does not come into the picture. Major issue. So, design for recovery and reuse. I could go on, but I think hopefully we will have some conversations tomorrow or the rest of the day that education has got to be an important aspect. Of course, this is very centric to engineering students, but there's also education for the public at large, which is also a responsibility that I think we have to ensure that the lay people, public at large, is aware of it. A lot of people think that if they put their beverage cans in a little box there that says recycling bin, that they're doing their job. There's a lot more to it. How many times have I seen people throw batteries, in the bin, not realizing that a lot of these things end up in landfills. And all landfills, even though they have geotextiles protecting them, they all leak. And the ramifications of putting things in landfills that will damage the water stratas that we drink. So education plays a big, big role. I've been focusing mostly on engineering education here. Policy. This is another big one, and hopefully we'll have more time to talk about it during the conference. Probably the best example I can give, which is a story. Lars Arnberg was a dear friend of mine from Sweden. He was at NTNU in Trondheim. He came on a sabbatical one year and spent a year with us. And I like cars and I like shopping for a car, especially if it's somebody else's money. And he wanted to buy a car he could take to Norway. So this was a wonderful opportunity to go shopping for a car with him. I was doing him a favor, actually, because he didn't know how to specify it. He wanted a Honda, I remember that, and we had it all configured. We went to the shop, to the store. He says, no, I cannot have a 3-liter. It's got to be 2-liter. I said, okay. But I said, you can afford this thing. No, it's taxes. Norwegians taxes are too high. It's got to be 2-liter. Okay, so we reduced it down to a 2-liter. But there was a 2.2-liter model, which was better, I thought. But then he said something even more poignant. He said, it's not so much the taxes. I don't want to be seen driving a car that's larger than 2-liter in my neighborhood. I thought it was quite telling. It's not about the taxes. So it's Pavlovian behavior. So one little rule in Norway, how it changes behavior of people, So governmental policies, rules really, really matter. I was fascinated to learn that in Norway, Tesla has the largest market share. And I don't know how they did it, but if you have a Tesla in Norway, you can park anywhere, and you don't pay tolls on the highways. Again, Pavlovian behavior. So policy has a lot to do with it. South Korea is a very good example. Nothing to do with cars, nothing to do with automobile or transportation, but food waste. Tremendous food waste in the older days. With few policies that the government put in, they have reduced food waste to very, very, over 95% is recycled today. Again, rules by which we're going to behave and abide by. Klaus Schwab, who is the founder of the World Economic Forum, had a wonderful art. Well, he's also written the book on Fourth Industrial Revolution, but he had a wonderful op-ed not too long ago. And I usually don't read slides, but I'm going to read this one. As a global community, we depend on the functioning of institutions and processes to manage our global neighborhood. So we need to think not as a national, the issues in Germany or in UK or in France. We got to think global. It's a global issue. The CO2 numbers that I gave earlier are not to any nation but to the planet Earth. There are a lot of policy issues that also we can talk about a bit later, maybe in the panel discussion, because time is running out. In the collection area, for example, performance contracts where you don't buy the car, you actually you're leasing it, and you have to return it back to the manufacturer. So the manufacturer has a responsibility to recover and reuse rather than the the buyer. So there's a whole bunch of topics of this sort that are all that come under the domain of policy. Then there is depreciation and accounting rules, which play a big role, because if you have a new process, let's say for steel making, and if a corporation has put in all kinds of money for a certain plant, they got to depreciate that over a period of the certain table. So things of this sort that have nothing to do with technology. And in terms of technology innovation, in the last couple of minutes here, just a couple of examples, walk the talk rather than just talk about it. We've done quite a bit in the aluminum recycling area. There's a lot of scrap aluminum now produced through shredders and automobiles that are shredded, and how to take that material, all of the scrap, the twitch, and to process it in such a way intelligently using sorting technologies, LIBS, XRT, XRF, as well as artificial intelligence, to create secondary aluminum alloys that are just as good, if not better, than the virgin material, and tremendous reduction of carbon footprint. So this is a company which is we founded with several of my PhD students, and they're doing amazing work on it. But it's all about taking scrap, creating waste, creating value out of waste. Another one is the electric vehicle batteries. You can, these slides are available to you. You can look at those later, but about 60% of them come from Japan, China, and Korea. But these things have to be recycled and recovered. And we formed a company called Ascent Elements with 3 of my students. I'm just a co-founder of these. I don't have any operational management role. And we're actually taking old batteries and making NMC 111, which is the easy one, all the way up to 811. The whole process is shredding, which is extractive metallurgy, leaching, hydrometallurgy, and creating batteries from the spent batteries. Last one is hydrogen. I know Dirk is going to talk about this tomorrow as well, but we're not going to be using lithium-ion batteries for trucks. We're going to be using fuel cells, so hydrogen production, hydrogen economy. A lot of material science goes into, and metallurgy goes into these fuel cells, from the electrocatalyst, from the catalyst layer, cell level, stack level, plant level. What happens at the titanium, iridium, the PM. There's a lot of wonderful opportunities that are going to come in and play a role in making all of this possible. So I'm happy to close, and hopefully it has set the stage for the conversations that are going to follow. And I've provided some context and some ideas and suggestions in 3 different directions. Thank you.
Brilliant. Thank you so much, Diran, for don't go because we've got a little bit of time for questions, and thank you so much for just accelerating a little bit at the end there to bring it to a close on time. So we have a few minutes for questions. Who would like to ask? Diran, a lot of food for thought there, for God's sake, a lot of metallurgy for thought. Who wants to ask a question? Don't be shy. It's early in the morning. Get excited. Ask questions. Some important things there. Yeah. Just say who you are, please.
Good morning. I'm Mike Lynch from Innoval Technology. Very much enjoyed the talk. Just looking at your 3 solution pathways then, are they all similarly weighted, or do you think you get better return from one or more of the others?
It's a good question. I would like to think that they're all important, similarly weighted. Education plays a major role. It's people who actually make things happen. But policy perhaps is the most difficult one to tackle, because if you think about who our audience is and who we are, we don't usually delve ourselves in that domain. And yet we abandon it, and we let the legislators and the lawyers to attend to them, and they may not, they're all good people. They don't mean ill, but they may not have the tools. to do it. So there has to be more conversation, more education, if you will, amongst the various tribes of the planet Earth, so they understand what the issues are. Unfortunately, there are a lot of rules and policies that are being made today by folks who have no clue what, who may not have as much of a clue as to what they're doing. So I think they're all important. They're all important.
Great question.
Thank you.
I think we may have to talk a bit. The whole thing of sustainability is it's and, isn't it? We can't afford to prioritize because we prioritize one thing and it's not going to work. There isn't one magic bullet or one thing which will sort it out. So
absolutely.
we've got to do and that's a major problem, really. That's one of the problems. Any other questions?
Diran, that was interesting. Except, as you know, in engineering today, the ability to work in the required courses to learn just the core of the field you're in, be it metallurgy or anything else, is very hard put and difficult. And the things you're suggesting, which fall into what I would call the more general aspects of society and the impact, do you see this as possible in a standard 4-year education with, possibility of a little more graduate work, as we're already barely able, at least in the United States with accreditation, to put in what we have to for the core of the subject?
It's a very, very, yeah.
It's another and.
It's a very good question, Marty. My answer to the dilemma is that you can't do one without the other. So how do you do it? So one thing that I can tell you that has worked, because I have some data on it, we did it for 10 years. About 15 years ago, the university president was concerned about retention, that, we're bringing all these engineering students in and spending a lot of money in admissions and all the processes, and only, about 30% of them after the first year drop out. They go into architecture, I don't know, by whatever. They don't stay in engineering because, as you said, it's so hardcore. So we started the GPS, Great Problem Seminars. So these are freshmen. They have no idea. They don't know much about fluid dynamics. They don't know much about thermodynamics. They don't have the core courses. So the seminars were in Feed the World. There was one on materials recovery and reuse and recycling. One on, I forget now, climate change on energy. And I thought we were going to improve retention. What we did, we empowered these students. They figured out, my God, this is an opportunity for us to do something about in our career, but I don't know nothing, so I better learn the stuff. So I think you need both. You need the motivation. You need to have the societal, human dimensional interest. And this generation, by the way, it really matters to them. They want to do something. So I don't think it's one or the other, as Brian said. I think you got to do both, but some things are going to give. Some things are going to give.
Challenge for the educators. Look, John, there are other hands going up, but I think we'll better call it to a close because we've got other speakers. There'll be lots of opportunity tomorrow afternoon to have and of course over coffee and everything. So let's move on. Thank you so much, Diran, again. Thanks.